welcome to a new module on linear systems and of first order differential equations and its particularly its qualitative analysis. So far in our all earlier modules, the topics we have completed the topics which are basically covered in a university syllabus. So now onwards the two of the main modules are one of the stability analysis, basically what we call it qualitative analysis, and qualitative analysis of linear system first we will do, and then in another module we will learn the qualitative analysis of the nonlinear system. So you can view this module is a precursor to the module on nonlinear systems and stability analysis, the trajectory behavior around an equilibrium point, etc. So that is the main aim of this module. It is not just the representation of the solutions which we can still obtain as a using the classical theory which we have already completed. We can use the existence uniqueness theory of the system of the things which we have studied in the previous module. Can apply in a similar fashion here, but the more important aspects about the study of the behavior, nature of the equilibrium points, behavior of the trajectories, because the solutions of the trajectories of ODE systems are solutions. So you can think it as a motion of certain particles. So I want to understand that. So first we will do it in this module about the linear systems and later in another module about the nonlinear systems. So you will also see the power of linear algebra and its diagonalization, the Jordan decomposition, its usefulness in analyzing these equations. So what we have done in one of our earlier modules, we have studied the first and second order linear systems. So we can also consider the nth order linear system, and what we will see quickly now, every nth order linear system is a special case of general nth order system. So how does a general nth order linear system? So let us look at the nth order linear system, linear equations. So let me give, before that is a linear system, a title to this module, linear systems and qualitative analysis. So that is the title of this particular topic. So how does a general nth order linear equation will look like? A regular linear equation will have the following form. You will have the nth equation which is coefficient 1, d power 5 by dt power n plus let me use the correct one, p1t into d power by n minus 1 y by dt power n minus 1 plus, if you go here you will get the final term Pn of t of y is equal to some gt. And if you are looking for an initial value problem, you can define as you have seen, will be seen rather, for n equal to 2 for the second order equation, not only the initial value problems, you can also define the boundary value problem, and you will see few lectures on boundary value problems of the second order equations in a different module. So for an initial value problem, so you need n conditions, say for example y at 0 is equal to y naught, y1 at 0 means y prime at 0 is equal to y1, etc. up to yn minus 1 of 0 is equal to say n conditions you need it. So that is a initial value problem. If gt equal to 0, this is called a homogeneous, gt equal to 0, then it is a homogeneous linear nth order equation, homogeneous linear nth order equation. What I am saying is that such a linear nth order equation can be converted into a first order system. How do you do that one? You put x1 is equal to y1, x2 is equal to y1 prime not y1, x1 is equal to y, x2 is equal to y prime, that is nothing but x2 is equal to y prime, x3 is equal to y second derivative, etc. up to xn minus 1 you will define to be xn minus 1 to be yn minus 2, and your last term xn is equal to the n minus 1th derivative, that is equal to d power n minus 1 y by dt power n minus 1. So, if you use this one and we can using that equation here. So, if you look at that, x1 dot is equal to y dot. So, the derivative of x1, the derivative of x1 here is nothing but y1. So, you can write down that way. So, if you look at that one, x1 dot is equal to that dx1 by dt exactly will be y1. I am using two notations, dot and 1 both are for the derivatives. So, you can write down this is y1, that is equal to x2. So, if you write x2 dot will be x3. So, if you go like that, you will get xn minus 1 is equal to dot xn minus 1 dot is equal to xn, and xn dot has to be recovered from your equation. X1 at that, if you look at here, this is what your thing, that will be, if you take this to the right hand side, you can write everything as, let me write down that you will get minus Pn into x1 minus Pn minus 1 into x2. If you go like that, the last part will be P1 into xn, and then you will also have your gt here. So, this is from the equation. This first n minus 1 from the definition, the last one will be from the equation. So, if you put this together here and if you define your xt now is equal to x1 etc. xn all evaluated at t, and you can write down your equation. If you combine all these, you will write your equation as x dot of t is equal to, you can write your matrix AT into your xt. You see what is AT, where AT is the matrix, is a special form of the matrix. You have a special 0 1 0 0, then 0 0 1, like that, 0 0, the last one here you will have minus Pn minus 1 etc. up to P1 you will have. This is correct. So, if you multiply this one AT into xt, AT into xt, so you will have this kind of system. So, that gives you a linear system of equation with the AT in this special form. See, AT is of this one, this is your AT. You have your AT like that. So, but this allows us to consider any general AT. You do not have to consider that way. So, general linear system. So, thus a general system can be written as initial value problem in this form: x dot of t is equal to a t x t. A t need not be in the above form. It can be a t will consist, the entries of a t will consist of functions, need not be the form given by the earlier thing, x at 0, or you can put it at any point x at 0 is equal to x naught. So, this is a general linear system. Of course, in general we are not going to concentrate on system such as this system. When a depends on t, yeah, plus some gt will also come, a non-linear term, where okay, you can have some non-homogeneous, this gives you a non-homogeneous. When a t depends on t, it is called non-autonomous, is called non-autonomous. So, if a t is equal to a independent of t, it's known, it's called an autonomous system. It's called an autonomous system. As you see, even in our first order and second order equation, for example, even when we are studying second order equation, when the second order coefficients are independent of the functions, you have seen the advantages and able to solve the equations completely. So, there is a larger advantage and many other, even the qualitative analysis you see the difference when you study nonlinear analysis part of this problem. So, for autonomous system is much more easier to study than non-autonomous system. So, most of these lectures, though in this module we will concentrate only on the autonomous systems and we try to represent the solutions and the stability analysis of that system. So, our major aim, if you look at case n equal to 1, that means a is equal to a, then the solution is, you know already, then the solution is x t is equal to e power t a into x naught, you see. So, our aim immediately we will see that we want to represent the solution for the system if possible of the form when it is for an autonomous system. So, our what is our autonomous system? Autonomous system is x dot of t is equal to a of x t, where a is independent of t, that is more important thing, and you will study the initial problem at any initial value is x naught, which is also a vector. So, this system we are always going to refer it to as 1. The important point here is that system 1 is a is independent of t. So, the whole aim is to represent the solution, aim represent the solution x t is of the form some exponential form, exponential. Here is what we are exponential form. Here what we want to recall the definition of an exponential of a matrix which we have studied already in the basic part of the module. So, if you have a matrix A, if A is a matrix, then e power A can be defined to be I plus A plus A square by 2 factorial plus etc. Where the series converges, that is what series converges in the set of all linear operators Rn to Rm. So, in this case, given a matrix, one can view it as a linear operator from the space Rn to the space Rm, and this is also identified with the set of all n by n matrices. That is what we are trying to say in this case. So, on this set of all linear operators from Rn to Rn, we have the corresponding itself vector space which has a topology. Under that you will talk about the convergence of this infinite series, and this e power a. So, note e power a is also a matrix. Note e power a is also a matrix. That is the important part of it. Okay. So, you can define e power a. In particular, we can also define for any t belongs to R e power t a. That is nothing but identity, again it is a matrix, plus t a plus t square a square by 2 factorial and so on. It is again an infinite series, and this series converges uniformly. In this case converges uniformly because there is a t parameter. So, again e power t a is a particular matrix here which you want to do that. Okay. So, here is an exercise. I want to give you start with an exercise now which you can do it easily. Define x t is equal to e power t minus t naught of a x naught. Note that e power t minus t naught into a is a matrix. So, that matrix will act on the vector x naught and x t is defined that. So, the exercise is that show that x t is differentiable in t, differentiable, and x t satisfies 1, x t satisfies 1, the system 1, system 1. What is a system 1? This is a system 1. So, this is the system 1. So, you just compute x dot of t, you can see that x dot of t is nothing but a of x t, and definitely x at t naught is easy to see that x at t naught is when t substituted for t naught, the first term here will be identity. So, x at t naught will be x naught. So, that way we have the existence. So, this proves this gives existence. That is what I am saying. So, you have proved the existence directly by construction. Of course, as I said, the existence and uniqueness can also be proved using the general existence uniqueness theory. But so, the existence which we have already have it. So, and we want to give you a uniqueness, a quick uniqueness proof. You can get the uniqueness using the general theory, but I want to give you a general easy thing. So, assume y be another solution, y equal to y t be another solution. Then what you have to do? To prove that, you have to prove that y t is equal to x t. That is what you have. X t is defined already. What is x t? X t is nothing but e power t minus t naught of a into x naught. That is what you have to prove it. Equivalently, so proving this is equivalent to that, I can take this out, e power minus of t minus t naught into a x y t, I will take that to the left side, is equal to x naught. So, what you want to prove is that this is what you have to prove it. So, this you have to prove it, that means left side is a function of t, right is just x naught which is a constant. So, you want to show that the left side is a constant and that constant is nothing but x naught. So, define in that case just the left hand side as Z t. You define Z t is equal to my e power minus t naught of a y t, which I can define. What I have to prove is that Z is a constant in t and that constant is nothing but x naught. So, to prove that constant, here is an exercise again for you. These are all simple exercises. Show that dz by dt is equal to 0. That is an easy exercise. When you show that dz by dt is equal to 0, then this exercise will give you z is equal to t is a constant. But what is that constant? But that constant has to be z at t naught. Z t is a constant already proved. So, it has to have the same value at t naught, but z at t naught by the definition here put t equal to t naught here. So, you will get this is nothing but y at t naught, but what is given to you? Y is a solution to your initial value problem and y at t naught is nothing but your x naught. So, you have your uniqueness in a quick way without appealing to the general theory. So, we have proved the existence and the uniqueness, existence by construction and uniqueness by direct application. The linear system, the autonomous linear system has a unique solution. So, we may wonder what more to be done here. The issue is that you already proved the existence and uniqueness. Again, if you go back to our second order linear equations, just obtaining solutions are not enough. Just like here, we have the representation of the solution x t in the form, we have the representation of the solution x t in the form e power t minus t naught a x naught, you have that one. So, the two of the difficult issues, two remarks, two difficulties here. One difficulty, the computation of exponential is very difficult. Computation, though you have a representation, but the computation is of exponential of a matrix is difficult. Exponential of a matrix is difficult in general. That is one point. The second point is that, as I remarked again, x t you have to think it is a dynamical system, is a solution to a dynamical system. In other words, x t you can think it as a motion of a particle. So, the important issue is that how this particles behaves, especially near an equilibrium point, which we are going to explain to you, and you will also learn about the equilibrium points later in the nonlinear theory. And so, what we are more interested is that the behavior of x t, especially near an equilibrium point, especially in particular the stability analysis of the trajectory. So, this formula does not reveal anything about x t. So, the second difficulty is that this formula do not reveal about the behavior of the trajectories, about the behavior of trajectories and equilibrium points, which we are going to study, trajectories and equilibrium points. You see, that is a whole thing. So, one is especially the computation of this thing, and second one is the trajectory behavior, and the whole module on this one and the nonlinear theory is to understand this trajectory, how does it behave, what are the equilibrium points, how whether you have the stability near an equilibrium. These are the questions from physics and engineering point of view. Okay. But then there are some matrices where you can have a computation easy. Example, if you want to see. Example, Suppose A is diagonal. Suppose A is diagonal. Okay. That means I write a diagonal matrix in this form. Suppose it is a diagonal matrix. So, diagonal matrix I will read only the diagonal entries lambda 1 etc. lambda n. This is nothing but what I mean by that is nothing but lambda 1, lambda 2 only along this diagonal lambda n, all the other elements are 0. So, I want you to give it's an exercise from again linear algebra which you would have done already. But I will also give you feeling what happens to the trajectories of the solutions with this A as the matrix. The thing is that you can immediately compute e power A will be again diagonal, but then entries with e power lambda 1. So, this is a small exercise which you can immediately do it. What you have to do is that you have to compute a square, a cube etc. If you compute a square, you will get the diagonal lambda 1 square, lambda 2 square etc. lambda n square, and for any a power n it will be diagonal of lambda 1 power n etc. lambda n power. So, and then add it and you get the matrix e power A immediately. But what does this mean when A is what does this mean when A is diagonal as far as our linear system is concerned? If A is diagonal, what does that diagonal system means to us? Diagonal, then it just says that x1 dot is equal to lambda 1 x1, x2 dot is equal to lambda 2 x2. If you rewrite the system and xn dot is equal to lambda n xn, you see. So, it is a decoupled system, there is no connection between, there is no interaction coupling between two variables. Any of the variables do not interact with the other variable, and each one is a simple equation, x1 dot is equal to lambda 1 x1, and since x2 etc. xn are not coming into picture, this immediately this is a decoupled system. This is what it says, decoupled. So, there is no problem immediately this decoupling system, you will give you the solution x1 t is equal to e power lambda 1 t into the initial value at the first component, that is all. If you go this way, you get your xn t is equal to e power lambda n of t, the nth component of your initial value. So, if you write this in the form, so this is equivalent to saying that if you write this e power xt is yeah, of course you have to change here. If I look my initial conditions at t naught is equal to x naught, so I have to change accordingly. I will change here accordingly. This will be e power t minus t naught into lambda 1. So, I will change here. This is what I wrote was for the initial value at the origin into lambda n x naught. This is just a multiplication. So, if I write these solutions, you have your x t is nothing but your diagonal of e power t minus t naught lambda 1 with entries this one, that is equal to e power t minus t naught of lambda n. This is a matrix, this is your matrix operated on x naught. So, that is nothing but your e t minus t naught a into x naught, you see. So, you have your solution and you have your complete solution if A is a diagonal matrix. Okay. And another interesting property with this, which will be useful for our analysis, we are eventually want to do more analysis. So, if the given matrix is diagonal, the corresponding ODE is a decoupled system. Since it is a decoupled system, is solving each equation, each n of the equations independently, because it is a first order equation in one variable, each one can be solved separately and then you can write down that solution. So, as long as the matrix is diagonal, you have no problem of solving it. Another property which I would like to recall here, the property is that in general for exponential map e power a plus b not equal to e power a into e power b. So, this property of real numbers is not true for general matrices, but if a and b commute, that is AB equal to BA, then e power a plus b, this will be useful in our analysis later, e power a into e power b. This you can verify. If a and b commute, you can prove that result. So, this exponential, one of the fundamental property of an exponential function in one variable is not true for exponential functions of the exponentials of the matrices, but if there is a commutation, and that is not contradicting. For real numbers, this is always true, AB is equal to BA for real numbers, and that is the thing. The another important thing, so I will recall today some more interesting things which is necessary for here. Another property which we want to call it property. Suppose B is of the form P inverse of AP. Such matrices are called similar matrices. As you know from linear algebra, similar matrices represent the same linear transformation. It is only according to a different basis you will have different matrices, but it will represent essentially the same linear transformation. Suppose B is equal to P inverse AP, then what is e power B? I want to know. So, this is a simple result again. I will leave it as a small exercise for you. If you have not done these things in the linear algebra, this may be the correct time to do that one. This will be P inverse of e power a P, you see. So, you have a nice representation. You can do this other way also. So, if this is equal to, this implies of course A is equal to P B P inverse, and that also implies e power a. So, you can write down, because P is an invertible matrix, P e power B P inverse. This is one important property which now we are going to use it. Under this linear transformation, this helps. So, you have a linear system x dot equal to Ax, but then this allows you to solve for solving for x dot equal to Ax, that namely the system x dot equal to Ax can be obtained by solving another system corresponding to B. So, the system 1 can be solved, system 1. Let me recall system 1. System 1 means Ax equal to x dot equal to Ax with x at t naught is equal to x naught. This is my system 1. Okay, this is my system 1, can be solved by solving system 2, namely corresponding to B. So, I introduce a system B equal to y is y at t naught equal to something, whatever it is, y at t naught is equal to some y naught, which we will solve. How do you achieve this one? So, recall. So, what is 1? 1 gives x dot is equal to Ax, but what is Ax? Is nothing but PB P inverse, PB P inverse of x. Now, put Yeah, so this if you call it here, you will get a P inverse of x dot is equal to B P inverse of x. Note that P is a invertible matrix with constant coefficients. So, P is independent of t. So, you can take inside x. So, you put y is equal to P inverse of x, that implies y dot is equal to by. So, you see, and what is y at t naught? Y at t naught is nothing but P inverse at x at t naught, that is x naught, and this is your y, this you call it to be y naught. So, you can solve your system. So, if you have two matrices are similar, the solution of the system corresponding to one matrix can be obtained by solving the a system corresponding to another equivalent. So, such two matrices are called the linearly equivalent. So, this leads to the concept of the concept of linear equivalence, concept of linear equivalence. So, you have a definition for this one. Two systems, the systems 1, the system 1, that is x dot equal to Ax is said to be linearly equivalent to, said to be linearly equivalent to a system, to the system 2, that if there exists an invertible matrix, P such that B is equal to P inverse of AP. See, that is the point. Okay. So, whenever two systems are linearly equivalent, you can go from one system to another system. What is so important about it? The important thing which you are going to see soon in next lecture or coming lectures, one property, the one important thing is that under linear equivalence, the nature of the equilibrium points or the stability of the trajectories do not change. For example, if a particular point is a equilibrium point, there will be a corresponding equilibrium point to the other system, and this equilibrium point is stable. You will see what are the kind of stability and stability are available soon, and then the other point will also be thing, and the behavior of how the trajectories will, even nature of the behavior, it will also remain the same. So, the nature, the first important property, right now you may not know it as we have not defined any sort of the concept of stability, but the important point which we are going to see, the nature, for example stability or instability of equilibrium points. We will tell what is equilibrium points. Equilibrium points do not change, under linear equivalence. So, what are these equilibrium points? So, recall. So, what is equilibrium points? You will see again, as I said, more on nonlinear systems about it, correct definitions again. Equilibrium points. Equilibrium points are actually solutions of the linear system, equilibrium points of x dot equal to Ax. Okay. So, equilibrium points, so though we call it point, it is a equilibrium, it is a solutions, steady state solution. Suppose Ax equal to 0, suppose x be such that, so let me calculate up not to confuse with the initial values, x naught be such that Ax naught is equal to 0. Okay. That means it satisfies the right hand side vanishes at that point. This implies if I define xt is equal to the constant x naught, constant will be a solution, That means if you have an equilibrium point, and if at t naught if the solution is at that point, then the solution will remain at that point all the time, it will not move from there. So, that is why it is a steady state solution. So, whenever you have an equilibrium point and the solution starting from there, it will not change there. So, for example, for linear system x naught equal to 0 is always an equilibrium point, always an equilibrium point. And when A is invertible, and this is the case when we are going to consider when A is invertible, 0 is the only equilibrium point, because if Ax not equal to 0, if A is invertible, x naught will be 0. So, if A is invertible, 0 is the only equilibrium point. You will see more examples in the next class. I want to set a kind of thing. Therefore, if you start a solution at the origin at time t naught, the solution will remain there. And here is where your concept of stability and equilibrium. In applications, you can never start from a particular point, you will always going to make error. So, the question is that if you start a solution at the origin at an equilibrium point, then the solution will remain there. Suppose you make an error and the solution is not starting at the origin, but then a solution is starting say at a point, initial point x naught, which is close to the origin. So, the question is that whether trajectory will deviate from there very far away, causing instability, because this is important in the point of view of applications. You will never be able to start at a particular point, you are always going to make error. And these kind of concepts also you have to know that when a solution starting near an equilibrium point will remain there, will go to the equilibrium point where it will move away from that, leading to various definitions, various types of stability, when especially when xt is a vector, it will have different components. Certain components will go to the origin, certain components will have the stability, certain components will not the stability, and all that can happen. And that is what basically in the qualitative analysis we are going to see that. The second point, so this is about the equilibrium point. So, we are going to initially we will give few examples even when A is not invertible, and then you can see the various equilibrium point and how the solution behave. Our more interest is that when A is invertible, in that case we have only one equilibrium point near 0, and we are going to study the stability analysis near the point near the equilibrium point. Okay. This is the first point. Second point of interest, the second point is about the change of variable. So, basically we are making a change. If you go back to our earlier analysis, the previous analysis, see if you go back to this kind of previous transformation. So, you see this is a transformation we made to convert the system x dot equal to Ax. to a system equal to y. So, there are two linear transformations basically. So, you have the transformations. So, you have transformations x going to y is equal to px, that is one transformation, and the other one y going to x is equal to p. Which one is the correct one? Both are fine. Y is equal to p inverse of x, y equal to p inverse of x, does not matter, you can replace that, x equal to p. Y are linear transformations, are, this is important, these are linear transformation, not some arbitrary transformations. Why it is linear? Because P is a matrix. Okay. Because it is a linear transformation, you can view this as a, that is an important one, can view it as a coordinate change, view it as a coordinate change. So, basically when you are considering coordinate change, so when you have some coordinates, you will be basically looking at two coordinate change, either x going to y or y going to x. So, you can see that if this is y1 y2, you will have a coordinate change x1 x2. Yeah. So, effectively when we are considering under linear equivalence x dot equal to ax and y dot equal to py, we are making a coordinate change. Under this coordinate change, the when you, for example, if a is invertible and x naught is an equilibrium point, and you will have a y naught is equal to p inverse of x naught will be an equilibrium point, that are the only equilibrium point you can get, that equilibrium points, and the stability of the system x naught is stable, which we will see, y naught will also be stable. That is what I say, it does not change. There may be a difference in movement of the trajectory, but the stability analysis, you cannot convert a stable equilibrium point to an unstable equilibrium point under linear equivalence. So, the fundamentally is a linear, is a coordinate change. That is what under this linear transformation one has to understand, and that is not surprising, because this linear equivalence is between two similar matrices. As you see that similar matrices represent the same linear transformations, and hence you should be able to do the same thing. Okay. So, what is our aim now? With these are general remarks about these are basically what is our aim. We should not forget about aim. What are we trying to do this one? See, what we have seen is that you are interested in solving a linear system x dot equal to x, and that you have a representation, you have a solution x at t naught is equal to say x naught, you have a linear system. And what we have so far discussed is that if there is a linear equivalence, that means you have a B is equal to P inverse of AP, and you have the corresponding system y dot equal to By, and y at t naught is equal to some P inverse of x naught, that is your y naught. And here the solution, as I said, that one of the major difficulty is the computation of the solution. Even though you have a solution x t is equal to, let me recall again once again, because this is the important point, x naught is equal to a into x naught. The computation of this is difficult. Suppose you are able to transform this under linear equivalence, you look for a linear transformation, so that the computation of e power t minus t naught into b into y naught, this is called y naught. So, this may be easy, this may be difficult, probably easy. You see, this is a situation we are looking at it. So, the question is that is it possible to find a linear equivalence so that the solution to y power dot is equal to by is easy to compute. When I say that solution to y dot equal to e power by is easy to compute, this is easily computable, and we have seen one situation where this can be computed easily when B is diagonalizable. So, this leads the question of diagonalizability of a matrix. Okay. So, that is where we are looking at it. So, that is where we are looking. So far we have discussed this linear equivalence, so that we are looking for a matrix B corresponding to A using the linear equivalence, so that B is diagonal. You see, suppose B is diagonal, that is the question. Suppose B is diagonal, lambda 1 etc. lambda n. So, then what is solution of yt? The solution yt is immediately you can write it, yt is equal to the diagonal of that one. So, diagonal e power t minus t naught lambda 1 etc. e power t minus t naught lambda n of this matrix acting at y naught. What is y naught? P inverse of x naught. So, this is what your yt, and what is your xt? Xt is nothing but P of yt. That is our transformation. So, you have your solution immediately P diagonal e power t minus t naught lambda 1 etc. e power t minus t naught lambda n of P inverse of x naught. So, you see you have your complete solution here. You can write down if you can question. So, that is why this is the question of diagonalizability immediately. So, the diagonalizability, the importance of, you would have seen the diagonalizability importance not only here when you are studying the linear algebra, whether if you can solve your linear system if the matrix is diagonal, because there again is a decoupling system, exactly what you are showing that. So, the question is that given a matrix A, does there exist an invertible matrix P such that B is equal to P inverse of AP is diagonal. If so, our problem is solved. If so, our problem is solved. Our computational problem is solved, because now the computation of e power b is easy because b is diagonal. But unfortunately, in general, the matrix need not be diagonal. The matrix need not be diagonal. Example, even when n equal to 2, that is simple, diagonal need not be diagonalizable, that is what I said, not diagonal. When n equal to 2, if such a matrix exists, is called diagonalizable. Example, you take lambda 1 0 lambda is not diagonalizable. How do you prove that? What is the kind of diagonalizable? You see, even such a matrix simple looking matrix is not diagonalizable. So, again let me recall from linear algebra, diagonalizability is equivalent to the existence of n independent eigenvectors. So, okay. So, remark, so recall diagonalizability is equivalent to the existence of n independent eigenvectors. This you have already seen in linear algebra. We also recalled some of these things in our basics. Independent eigenvectors. So, here is an exercise for you for the problem for the above matrix. For this matrix, for show that it has only one eigenvector. Show that it has only one eigenvector, one independent eigenvector. Do you see that? So, when you are studying the linear systems, our main aim is that given a matrix, can we have a diagonalizability property. The moment your given matrix is diagonalizable, that means you can find a matrix B. So, that is a corresponding B, you completely the system is solved. If the system is not diagonalizable, what can we do about it? This is where the linear algebra and the Jordan decomposition comes into help, and we will use that to understand the how much we can do it if the matrix is not diagonalizable. What we will do in the next lecture? We will do a complete analysis in a 2 by 2 system, because 2 by 2 system, the possibility, what are all the possibilities is easy to classify. Even in higher dimensions, the Jordan decomposition tells you the best possible way you can do it, and but we will spend a more detailed study in 2 by 2 systems, and in the process we introduce the concept of phase plane and phase portrait, and then the various stability. So, we will have a complete analysis in the next lecture. Thank you.